Let's get started talking about Math 105, Section 5.2, and we are modeling with logarithms and exponentials. And how do we apply these properties that we've developed in our previous video series? And I think one of the classic examples here will be just solving some exponential function exactly. And so maybe we'll have something that looks like this. We'll say P of x is equal to 7.2 2/3 x minus 4 over 5. And I want to solve this. Now, if I look at this, this 2/3 to the 1/5 power is my b value. And so this is an exponential decay. And so let's solve exactly when p of x is equal to 10. And what's going to happen here is I need to make sure that we isolate our exponential before I apply logarithm. So the first thing I'm going to do is I'm going to divide by 7.2 on both sides. And now I can apply logarithm to both sides, having the log of 10 over 7.2 is equal to the log of 2/3 raised to the x minus 4 over 5. Notice that that 2/3 is being raised to that power, and that power is inside of logarithm, letting me know that now that power can come down. I have x minus 4 over 5 times the log of 2/3, and that's equal to the log of 10 over 7.2. Excellent. Now, the dream is to begin to solve for x. So I'm going to divide by log. I'm going to multiply by 5. So we can have log of 10 over 7.2 divided by the log of 2/3. And I'm also going to multiply by 5 on both sides, leaving us with x minus 4. And so our final step is just to add that 4 on each side. X is equal to this trash, the log of 10 over 7.2, divided by the log of 2/3, all of which is multiplied by 5, and then we add 4, and we are complete. Well, let's suppose I have two different competing populations and I want to know where these populations or when these populations are going to be equal. So suppose I have 3e to the 0.7x, and we'll have that equal to population 1. And we'll have another population, we'll have this at 10.96 to the x minus 2 as my second population. And the dream is to know when these populations will equal each other. Well, first we can point out that we're starting at 3 and our population is growing by 70% continuously. On the other hand, this population, when it's year 2, it's at 10 and it's decreasing by 4% each year. So we're going to start out by setting these two equal. 3e to the 0.7x is equal to 10 to the 0.96 raised to the x minus 2. And I think there's a variety of ways to attack here, but my methodology is going to be applying natural log to both sides. And in doing that, the hope is to get rid of that e. Natural log on one side, natural log on the other. Notice that the 96.96 has that x minus 2 as an exponent. So, can I have murder occur here? And the answer is not yet. And the reason we don't is because I don't have the natural log and the e alone. I need to somehow split this up, and we can do that because I have a product. We'll write that as natural log of 3 plus the natural log of e to the 0.7x. And this will be equal to the natural log of 10 plus the natural log of 0.96 raised to the x minus 2. Let's keep going, friends. At this point, we can see that murder occurs, and I'll have 0.7x, natural log of 3, the natural log of 10, and I can bring this x minus 2 down as our linear function. So we can see that we're going to start thinking about getting all the constants on one side and the x's on the other. Let's subtract natural log of 10. Let's subtract 0.7x. But the other thing that I want to do is I want to distribute this natural log of 0.96 into this. So we'll have natural log of 3 minus the natural log of 10 is equal to negative 0.7x plus natural log of 0.96 times x, that's the distribution there, minus 2 natural log of 0.96. I don't know why I wrote the x at the end or the x at the front. It doesn't really matter. I'm going to add this term over, and then here I have an x on both of these, and we can factor. So if I factor out an x, we'll have negative 0.7 plus the natural log of 0.96. And over here, natural log of 3 minus the natural log of 10 plus 2 natural log of 0.96. Ran out of space. We'll take this terrible thing, we'll divide it by this terrible thing, and so we'll have our final answer, natural log of 3 minus the natural log of 10 plus 2 times the natural log of 0.96, all of which is divided by negative 0.7 plus the natural log of 0.96, and that is x, and we're out. This is not the only way to attack here. There are many people that are happy to take this and get all of our leading coefficients to one side initially so that they don't have to think about this step on both parts. And so you could just as easily say you had 3/10 e to the 0.7x is equal to 0.96 to the x minus 2. And then take natural log of both sides, splitting this piece up. But keep in mind, natural log of 3 over 10 is the exact same as natural log of 3 minus the natural log of 10. So we're going to arrive at the exact same answer. You must be careful when you're working through these solutions that your answers might not look exactly like mine do on Canvas, and that's okay. Punch your answer into an adding machine, punch mine, and you ought to get the exact same thing. Let's talk about one last type of problem here. And maybe the problem will have a story that starts out like this. Suppose P of t is equal to 7.4 e to the 0.7 x plus 2. This means 2 days before our experiment started, the population was at 7.4. But we have a continuous growth rate of 70%. And what I want to know is, I should probably have a T there, how fast is the population growing, each year? I guess I should probably have a better term there. By what percentage is our population growing each year? And the idea is we're given a k value here. We know that our growth factor is equal to e to the 0.7, but we're not asked for a k value. We're asked for by what percentage is our population growing each year. We want r. So we know that b is not just equal to e to the k, b is equal to 1 plus r. And let's solve for r as a percentage. E to the 0.7 is equal to 1 plus r. I can subtract e to the 0.7 minus 1 is equal to r. And now as a percent, I can multiply by 100. And this is my yearly growth percentage, yeah? my yearly growth rate, which is different than my continuous growth rate. This number should be smaller than 70%. And if we want, we can punch it into our adding machine and see that it is. Let's do one last problem similar in nature to this. Let's have some population, Q of t is equal to 7,500 times 1.23 raised to the 2t minus 4. Now, I think before we do anything, we should probably figure out what A is equal to and what B is equal to. And the idea here is the question will be, what is the continuous growth rate as a percentage? Yeah? So we got to figure out what our growth factor is. And so we'll have to do some manipulation. We can certainly get A by putting 0 in. The 0 goes there, so it's going to be 7,500, 1.23 to the negative 4th power. But we can also manipulate that 7,500, 1.23 to the 2t times 1.23 to the negative 4th. And now we can see that our A value is both of those terms. How do we get B? Well, B is anything that's being raised to the t, and with our properties of exponents, we can see that B is 1.23 squared. So we have B. We want to know the continuous growth rate, and that is a K question. What do we know? We know that B is equal to e to the K. So I'm going to take natural log on both sides. Natural log of e to the k is equal to the natural log of 1.23 squared. Now, I know you could bring that 2 down, but I don't really care. I just want an exact answer that I can put into web work. And so k is equal to the natural log of 1.23 squared. Now, this k is not a percentage. It's a decimal. So we're going to multiply by 100. So k as a percent is equal to 100 natural log 1.23 squared. And once again, we are out.